So today I will talk about Symbolic Pathfinder, which is a software analysis tool, and which was motivated by the many bugs that exist in software and the need for automated tools to find these bugs. There is an echo, okay, I hope it's fine. And there, as probably you already heard from previous talks, there are many approaches to finding errors. The most common approach is testing, which is a well-accepted technique, but it may miss errors. More sophisticated technique is model checking, and you heard a tutorial on Java Pathfinder, which is a model checker for Java bytecode. So in theory, it's automatic and exhaustive, but it cannot really scale to very large programs, although a lot of progress has been made. And there are also techniques that are in the realm of static analysis, and they are typically more scalable than model checking, but the reported errors may be spurious. And Symbolic Pathfinder is somewhat related to all these approaches. So it's related to testing because it can generate tests. It's related to model checking, actually it's built on top of a model checker. And also it performs a kind of part of a static analysis because it performs symbolic evaluation that a lot of static analysis tools perform, but it doesn't do the let's say generalization or abstraction part that is typically done in static analysis. So in particular, symbolic execution is a well-known program analysis technique that was proposed in the 70s, and it executes programs on symbolic rather than concrete inputs. And the idea is that these symbolic inputs represent multiple concrete inputs, and then you can execute a program based on the symbolic inputs that in some sense accounts to executing the program on multiple inputs at the same time. And the analysis maintains a so-called path condition that encodes conditions on inputs that follow the same program paths. And these path conditions basically are collected from the different conditions in the code and are checked for satisfiability using off-the-shelf solvers. For instance, we use Z3 from Microsoft, but there are many other solvers that can be used. And if a path condition is found to be non-satisfiable, the analysis stops from that path because intuitively there are no inputs that can follow that path. So effectively the analysis explores only feasible paths. And the byproduct of this use of constraint solving is that the obtained solutions can be used as test inputs that exercise the different paths through the code. And there are many analyzers that perform this kind of symbolic execution. Usually there is, one puts a bound on the execution depth to account for loops and recursion. And I'll show an example about that. And the typical applications are test input generation, as I said, or error detection, but there are many other applications, and some of them I'll try to touch upon during this tutorial. And there are many tools that perform this kind of technique for C and C++. We have Sage, Dart, CLI is the most active currently, and many other tools, and I'll talk about Symbolic Pathfinder. I'll first illustrate symbolic execution with a simple concrete example that you might have seen also in previous talks. So on the left-hand side, I showed the code of a simplified Java code, let's say, that takes in, two inputs, X and Y, and if X is greater than Y, it performs some calculations to swap the two integers. And then we also have an assert false statement that is guarded by the second if statement. And the idea is that if the two inputs were swapped correctly, that assert false should not be reachable. So how would one check such a property on this code? So using testing, you can create two values for x and y. Let's say you assign 1 to x and 0 to y, and then execute the code, and the result is one trace, one path through the code, on which we have that the assertion is indeed not reachable because yeah, the second if statement, the then branch is false. Now, in contrast with symbolic execution, as I said, we start with the symbolic values. So here, the symbolic values are denoted with big X and big Y. And the result of symbolic execution on these symbolic values is a set of traces rather than just one trace. And this set of traces can be organized in a so-called symbolic execution tree. And the nodes in the symbolic execution trees are represented by the symbolic values of the different variables through the code. And then there is some branching that is due to encountering conditions through the code. So for instance, when we start the execution with the path condition, which is true, and then we execute the first if statement through the program, and now the analysis will basically systematically try to execute both the then and else branch through the code. And on the else branch, the path condition is updated. So the analysis remembers in the path condition which decisions it took. So the path condition is updated with the condition for the else branch, which in our case is big X less or equal than big Y. And for the then branch, the path condition is updated with big X greater than big Y. And then the computation is performed in terms of those symbolic inputs. So variable X becomes the sum of the two symbolic inputs. So it's big X plus big Y. Then Y becomes big X, and variable X becomes big Y. So as you can see, the swapping was successful. And then there is a second if statement, which is evaluated. And again, the analysis tries to evaluate both branches through the code. And on the true branch, the path condition becomes big X greater than big Y and big Y greater than big X, which if we feed to a constraint solver, it will say this is not satisfiable. So at this point, the analysis will end. So the assert false is not reachable on that branch. And for the other branch, for the false branch, the path condition is updated, it's satisfiable, and the program ends successfully. So the result of the execution in the end is two feasible paths, and one can solve the path conditions corresponding to this to the leaves in this tree, and the obtained solutions can be used as test inputs that exercise the two feasible paths through this code. Now let us consider another example. So this is a very simple example where we have a loop, and we have a method called test, and it takes one input, which is n. So n is symbolic. And inside the code, we start with a local variable that is initialized to 0. And while executing the loop, x is incremented. And if x reaches n, the program exits the loop and terminates. So I would like to ask the audience. So what do you think? Will this program always terminate? Hello? Sorry, can you hear me?
Yeah.
I think it's nothing.
You think it is what?
Nothing, I think. Because n is 0 and it started and the while is rejected. We did not assign anything.
So if you start with n is 0, what will happen? Will the program terminate or not?
So
Yes, it will terminate.
it's a Java program, right? So both are signed the way I don't have any strange behavior with. Well, we might have overflow, but then it eventually is less than n. Unless
So my question is, will this program always terminate or not? It's the simplest loop. I would say confidently that it terminates, no?
yeah, so even if n is the highest possible integer, if it's also int, it's not like unsigned where it can be greater than x forever.
Yeah, but I mean, I'm not talking about a symbolic execution, but if I execute this program with
already input and terminate.
Great. Yes, we agree that it terminates always. Yes, in Java semantics, even if n is very large, it might take a long time, but it should terminate. I mean, otherwise, how will we ever use any kind of loop in Java? But let us see how we analyze this symbolically. So it's a bit interesting that even this simplest program might lead to a very large number of paths, and this is what I want to illustrate here. So let us see how we will execute basically this program symbolically, and we start with a symbolic value for the input. So we only have one input n, and the symbolic value is big S here, and the path condition is true. And then basically, as we have learned already, so in the state will also maintain the values of the concrete states. And we first execute the condition of the loop, and there are two possibilities. We either stay in the loop or exit the loop, and the path condition will, the analysis will record this information systematically. So in one case, the, one path corresponds to exiting the loop because S is 0 is greater or equal than S. But in the other case, when 0 is less than S, or anyway, S greater than 0, we stay in the loop. X is incremented, so X is concrete, it becomes 1. And then again, we execute the condition of the loop and so on. So as you can see, a naive symbolic execution of this piece of code can lead to a very large or possibly an infinite symbolic execution tree. That's why in practice, we put a bound on the execution depth or on the number of conditions in the path condition, which in some sense give you an idea of, how many conditions along the path with symbolic values have been evaluated. And as a side comment, so just listing, for example, the line of codes in the code that was analyzed is not always the best metric for, an analysis tool, because if you have loops, even if you don't have too many lines of code, unless you do something smarter about the loops, you still have a very large, possibly unbounded number of cases that need to be analyzed. So after this short introduction of the basics of symbolic execution, I will talk a bit more about the tool itself. So our tool performs an analysis similar to what I showed, but for Java bytecode. It is an open source tool, and I put at the bottom of the page the link on which you can find the tool. And when analyzing something a bit more complicated like Java bytecode, you have to worry about many other things. So how, okay, it's clear how we can handle numeric inputs, but what about if the inputs are data structures such as lists or trees or arrays that have symbolic elements? And also, of course, Java has multi-threading, and also this kind of analysis is amenable to analyzing methods. So not just the whole program as is typically done, let's say, for example, in a model checker, because for methods you can assign these symbolics, but then of course methods can have many different kind of types for arguments. So you then also need to worry about strings. What does it mean to have constraints for strings, and how do they interact with numerics and so on? Do we even have decision procedures for all these different types? And a lot of work over the years has been put in this tool to handle many of these cases, and I will talk about some of these problems and how we handle them. There is also support for more sophisticated analysis that goes beyond the kind of analysis that I have shown, that also performs some quantitative reasoning. So not only, to say yes or no answers, I have an input or not, or this assert false is reachable or not, but how many inputs reach a certain statement, and this information can be used for different kind of analysis, and I'll talk a little bit about that. And another point that is also common with Java Pathfinder is that Symbolic Pathfinder inherits a lot of library models from Java Pathfinder, but it also implements some library models for particular operations. For example, operations on big integers, or special treatment of math library calls can be done more efficiently if you have models for that. Through this tutorial, I will try to touch upon some of these issues, but not upon all of them because there are many. And I will start by giving more details. So you already know about the Java Pathfinder tool itself, and perhaps you are already familiar with choice generators and the listeners, and that we also use in our tool. And Symbolic Pathfinder basically initially was implemented as an extension of Java Pathfinder, but it has grown and grown. So now probably the code base is, yeah, I don't know, quite large. Yeah, right now we maintain it as a separate, I don't know, cousin project, I guess. I will start first by highlighting one of the initial innovations for this work, which is handling data structures. And we had a technique that was called lazy initialization, and this was presented at TACAS in 2003. And also we had some papers at ISTA and later about this work, that also over the years, these papers won also several awards. So they were kind of used also by other people in their work. And the idea is that we use the non-determinism that we inherited from the Java Pathfinder model checker to handle aliasing. And I'll illustrate this with simple examples. On the left-hand side, we have an implementation of a singly linked list. We have class node with integer elements denoted lm, and next points to the next element in the list. And then we have a method swap node that is supposed to swap the first two elements in the list under certain conditions. So if first element is greater than the second element, this code is supposed to swap the two elements and then return the list. So what are the arguments to this method? The arguments are basically represented by the implicit this parameter in Java. So the implicit argument is a linked list of type of class node. And then applying the symbolic analysis over this method will generate the results showed on the right-hand side, which basically summarize all the possible input-output configurations of lists for this code. So I'll explain a little bit more about this, but basically we show different linked lists with symbolic elements. We also show the constraints on those symbolic elements, and the yellow blob represents in some sense parts that were unexplored by the analysis because they, in some sense, they do not matter for the execution of this list. So how do we do this analysis exactly? Intuitively, we start with list that has uninitialized inputs, and then we lazily concretize that list into different kind of lists according to aliasing possibilities in the inputs. And after we concretize the list, we apply the normal Java semantics to perform the operations on the reference fields, and then we do the usual symbolic execution for the numerics. So this concretization is also be similar to, for example, the focus operation used in some static analysis, and we also use a similar idea here. So here I just show some basically a snapshot of the analysis. So suppose we are at some state where the configuration of the heap, which for us, for this simple example, is just a representation of the list. It has two elements, E0 and E1, and T is pointing to the second element in the list, and E1 next points to a yellow blob, which basically means that it's uninitialized or is symbolic, if you want. So how can we perform? We want to execute next equals t.next. So how can we do that? We first examine the value of t.next, and we see that it is symbolic, it is uninitialized. So before proceeding with execution, we first initialize it and exploit the non-determinism from the underlying model checker to initialize the list to all the possible concrete next elements that would allow, you know, the aliasing in the input. So one way to concretize next is to assign it to null or to another element that points to a blob. So we don't know the rest of the list, but we know that the next element pointed to by E1 is now concretized, and the last two elements are, you know, represent different configurations according to different, you know, cycles in the input list. And once we have concretized this, we can execute move. So next becomes t.next, and once we have that, we can use the normal symbolic execution that, for example, reasons about constraints on E0 and E1. So this is just a super high level to give you an idea about how one can handle these kind of data structures. But yeah, there are more details in the papers. So going back to more concrete ways to run Symbolic Pathfinder. So these are some old instructions on how to run Symbolic Pathfinder. So you can find, you would need both JPF Core and JPF SymDC that are available from the Symbolic Pathfinder website. And you need to create some site properties, and then you can run them, and they are similar to also how JPF Core is run. Now, admittedly, and you have heard the talk, I think just before my talk, that we are transitioning to a Gradle build. So, and actually we got rid of the site properties, and we try to simplify the way one can run Symbolic Pathfinder, and hopefully, actually after this ASC, we will update and also, yeah, to that build, and we'll also update the documentation. So hopefully it will be a little bit easier to set up and to run. So please follow the news on the website. So some more details about the tool. As I said, there is symbolic search space may be unbounded, so we need due to loops and also recursion, and we need to put a limit on the search depth, and there are configuration options to do that. And how we implement this exactly is basically we replace the interpretation of bytecode, of some of the bytecodes with some non-standard interpretation that performs this kind of symbolic execution or lazy initialization. And the way this is done, we use the attributes that, again, we have them from JPF Core that kind of introduce meta, they can be used to store meta information about values in the state that is analyzed. And we use these attributes to store the symbolic information, the symbolic expressions computed during this non-standard interpretation, and they are propagated during analysis. And I'll show some concrete examples. An essential mechanism for us to implement symbolic execution and lazy initialization is to use non-deterministic choices. So as you remember, we have that symbolic execution tree, and then you have to, you know, examine both possibilities. So you can see that as a non-deterministic choice in the search space. And we use the choice generators from Java Pathfinder to implement those. And, you know, but in addition, we also need to maintain the path conditions. So whenever a non-deterministic choice is made, you need to update, we need to update a data structure that maintains the path conditions through the code. And actually, the more concretely, how we do that, we associate a path. Basically, the path condition is distributed along the path, and with a choice, we associate the constraint that was made. So in order to recover the full path condition, you have to walk back along the path and collect all the constraints along the path and solve for them and so on. We also use the listener mechanism for Java from Java Pathfinder that is used to, for instance, collect and print information about the search, print generated test inputs or test sequences. And in the last few years, I would say the heavy use of listeners was to implement different heuristics that kind of influence the search and so on. There is a mechanism for modeling these native libraries. So for example, as I already mentioned, we captured the math library calls and send them to constraint solvers. And there are many other different modes to execute the tool, and I'll get back to it a bit later. So just to give you again at a high level idea about how this analysis is implemented. This is an example for IADD, which is a bytecode that implements addition for two integer values. So on the left hand side is the snippet of code that is inside JPF, inside Java Pathfinder, that implements basically the concrete execution of this bytecode. So there are two values that are popped. There is a stack that is maintained. There are two values that are popped, and then the result is pushed back. This is at a high level what this IADD bytecode does. And now on the right hand side, I'm showing the symbolic counterpart of this execution. So basically this IADD will extend the concrete or the class that was inherited from Java Pathfinder from JPF core. But now instead, so the first thing that we do, we try to see if the two values that are fed to, that we need to add are symbolic. And there are quite a few ... but you can look at the code to see. The idea is that we first look at the attributes of the the first two elements that are on top of the stack, and if these are represented by this sim v1 and sim v2, and if they are null, it means that the two inputs are actually concrete, so we can just execute the original code. But if they are symbolic, we need to do something else. So in this code, which is the original implementation of symbolic execution, we would first pop the two values, but then we will push an arbitrary value because we are in symbolic mode and we don't care about the concrete value. And then let's say we push 0, and then we'll set the attribute of the result to what? To a new attribute that is represented by an expression, which is of type plus. And it has two, the two symbolics as the operands of that expression. And then we will continue. Now we also have a concolic execution mode that is not very well known about in the community, but we hope to document it better, that performs a kind of symbolic execution along concrete paths. And the difference, for example, would be that here, instead of pushing 0, we would push the actual concrete values. But so we also have that mode. So we have, so in reality, if you take a look at these bytecodes, the implementation is more complicated than just this. Now again, this is a high level, conceptual description of how a conditional is performed in symbolic execution. On the left hand side, I am showing how the condition for greater than equal is implemented. So how that is happening is in the concrete interpretation, one pops the first value on the stack, and if it's greater or equal than 0, it will go to on one branch, and otherwise it will go to a different branch. And On the right hand side, I showed the symbolic representation. So similar to the case of addition, we first examine the attribute of the condition. If it is concrete, then we delegate to the concrete execution. But otherwise, we need to use the choice generators to basically introduce a non-deterministic choice that would allow the analysis to examine both branches or both possibilities through the code. And this is a bit of a complicated code, but at a super high level, we create a choice generator. We basically here we introduce, there is a complicated mechanism to execute this, but technically, we are now allowed to, this instruction now will be executed twice during analysis, once for the then branch, once corresponding to one choice versus the other one, false versus true, and for each case we will add the corresponding constraint to the path condition, and then basically we will also have a call to constraint solver, which is hidden under pc.satisfiable, that so under the hood it will call a constraint solver that should again be configurable through different options from the command line. And then this would tell us either if it's not satisfiable, there is an instruction that tells JPF to backtrack at that point to stop execution on that branch, or otherwise that path condition is good. So we will kind of set the path condition for the current path. So this is again very abstract, and if you look in the code, we also have some optimization. So in certain cases, you can get away with not introducing a deterministic choice, and so it's a bit more complicated in practice. But again, if you are interested, you should study the code. So another mode is string analysis, and as you may know, is Java is a very popular language still for developing web applications, but these web applications may be susceptible to many vulnerabilities, and I list some of them on the slide. And then many of these vulnerabilities are due to errors that are performed by the string processing. So there might be incorrect or incomplete input validation and sanitization. So of course, there is a lot of interest in performing a kind of symbolic execution when the inputs are strings. And I believe you heard a talk earlier at the workshop about an effort along these lines. So I will not spend too much time on it, but I show here an example from the code that we analyzed in the past. So basically this shows a piece of Java code that takes as input a string that represents a command, and then there is also some local path that has some constant value, which is also a string. And then on the right hand side we show the path condition generated from analyzing this code. So the idea is to give to show a bit how that these constraints can become quickly very complicated. So they have talk about different operations over strings. They also talk about comparisons with numerics. You can also have symbolic values that are numerics, and this interplay between different kind of constraints makes the analysis quite complicated. So these are some older results, and actually we do have current request to integrate the latest work that was done for string analysis. So we will do that after ASC, but basically quite a bit of effort was put into integrating different decision procedures for string solvings. So we had some older versions of Z3 that were handling some kind of a subset of the operations. A lot of effort was put by a group from Santa Barbara, from Tevfik Bultan's group, and they developed a solver called ABC, which actually can solve constraints for strings, but also combinations of strings and numerics. And for us, it was also interesting because it can perform something called model counting, which is can be useful for more advanced analysis that perform quantitative reasoning. And we also have a branch that, and I will tell you some details about the resources, where we also try to perform now string solving, but then to use the basically low-level implementation of strings, and then to use basically theories for bit vectors to handle them. As I'm not sure I'll have a lot of time, I will not have time to go in depth with a lot of applications, but I will give you a high-level overview. So still the main challenge with Symbolic Pathfinder and many tools of this flavor are related to scalability, and I would also say related to usability. And while for usability we should do more, scalability is it's still a very hard challenge, and there is still a lot of research to address this problem. So I list quickly here some of my previous work that addresses this challenge. So we have done old work on exploring the state matching capabilities of Java Pathfinder in the context of Symbolic Pathfinder. Of course, the challenge there is that a state maintained by Symbolic Pathfinder, is not just an assignment of values, but we have symbolic values and constraints that represent sets of states. So we have defined some, then state matching in some sense becomes subsumption checking. And then we also explored applying some abstraction principles over the symbolic states computed by symbolic execution. And we had some old work about that. Another work that I'd say is still relevant is parallel symbolic execution. So exploring these different paths through a tree can be done in parallel. And with more recent work with Yannick, we have basically combinations of fuzzing and symbolic execution. I would say concolic execution, which again are very amenable to parallelization. So probably future projects can also build on this. I will try actually to now give an overview of different applications and modes. And I have many slides on this, but I don't think I'll have time. So I really want to point them out to you, and then maybe we can discuss, because the idea is also to inspire students who would like to collaborate and contribute, and or I don't know, to inspire them in their research. So the classic application is test input generation. We have many different incarnations of it. We also have test sequence generation. So we can generate basically sequences of methods that exercise a class in different ways. Another classic application is bug finding. So you can find assert violations or uncaught exceptions and so on. And the byproduct is that in theory, at least, we can also give you the inputs that lead to those bugs. As I said, we have a mode of mixed concrete symbolic execution where the idea is to solve the symbolic constraints and use the solutions to execute external libraries. So this is slightly different than concolic execution, which we can also now perform fully, where the idea is that you collect constraints along concrete inputs, and then you systematically, you organize those into trees and systematically or heuristically solve the constraints to explore that tree. And Yannick has done a lot of work in that direction. We have a lot of work that is not under the Symbolic Pathfinder repository, but in a separate repository, but perhaps we should move them all under the same repository so people have easy access to the code base. So we have done a lot of work on complexity analysis, where the idea is to use symbolic execution to synthesize inputs that lead, for example, to the longest path, or more generally to a path that has a high cost according to a cost function. And then we have heuristics that try to maximize that cost. We also have done a lot of work on probabilistic reasoning, where the idea is to use the constraints collected with symbolic execution and then use off-the-shelf model counters to solve those constraints and to get an estimate of the solution spaces for those constraints. And the byproduct of that probabilistic reasoning is actually security analysis, because you can do a form of quantitative information flow analysis to obtain estimates of the leakage that you obtain. And we have a project that performs this kind of analysis, in particular for vulnerability, that is called side channel vulnerability. Together with Yannick, we have done a lot of interesting and I would say very promising work on combinations of symbolic or concolic execution with fuzzing. So we also have a fuzzing tool. So fuzzing, as you may know, is an automatic testing technique that applies mutations to inputs to try to exercise these different parts of code. And fuzzing is in some sense easy and very successful, but it's hard to for example, exercise conditions that have equality, because it's hard to invent two symbolics that are exactly equals just by mutations, for instance. But symbolic execution would be good in such cases. So we are not the first researchers to observe that combinations of, more fuzzing-like techniques with more expensive symbolic execution techniques can help both. But our efforts were focused on these non-standard properties, so not just bug findings, but again, for example, complexity analysis. Or we have also spent time and effort to develop differential analysis. So how can you analyze two versions of a code and basically generate inputs or quantify, the input spaces that exercise the parts that are different in the two versions. And last but not least, I would say the effort that is also very related to my current interest is on symbolic execution for neural networks. And we have a project called NeuroSPF. And I have many slides for all these applications, but I don't have time to talk about all of them. I'll just highlight some of them, and then I'll give you the resources where you can find more information for all those projects. So this is one application is test generation and bug finding, and this is one of the earlier success stories. So we analyzed the prototype of component of NASA control software called Onboard Abort Executive, or OAE. This piece of code was initially written in C++, but then somebody translated it into Java. And so the structure is, so the purpose of this OAE, so this is run during a mission, let's say on a rocket, and it monitors different kind of inputs from different sensors on the rocket, and it checks flight rules. And if, for example, pressure or speed or different combinations, violate some flight rules, then the piece of software determines that maybe it's the case to issue an abort, and then it has some logic that selects the, the class or the code for which abort to issue, and then it picks the highest ranked abort and it issues the abort. So this is a complicated piece of software in the sense that it has many flight rules, and also the logic for picking the highest ranked abort is complicated, but on the other hand it's not very large. It doesn't have super complicated data structures. It doesn't have concurrency, so it's quite easy for symbolic execution. And then, so basically we analyzed this code to generate tests to obtain full coverage of the code. And this was one of the earliest success stories, in the sense that compared to manual testing, which was time consuming and they missed some important cases, this was automatic and it was very fast. And also they used the test in a regression setting, and they found actually a major bug in the new version. So we were really helpful. A little bit about the sequence generation. I think this is maybe less known, and we should do a better job at documenting it. But we have basically a symbolic sequence listener that prints non-redundant method sequences of a given sequence length for Java class and based on the public methods. And also it has some nice visualization of basically the object state machine that is represented by all these, is like a summary of all the generated method sequences. And since I don't have time to go through any of this, sorry, I just want to go to the end and show the resources. So I would like to end with an overview of the resources. So the GitHub address for the Symbolic Pathfinder is listed first, and then we have many of the projects and applications that I mentioned are under a different repository. ISTAC is the name of a project that we had, and it was about complexity and side channel analysis. So there you can find Kelinci, which is AFL-based fuzzing tool for Java. Badger is a complexity analysis tool that combines fuzzing and symbolic execution. diffuzz is another tool that performs differential fuzzing for side channel analysis. I realized actually we have another tool that performs differential symbolic execution, differential hybrid analysis, but it's not listed here. We also have a tool for algorithmic complexity analysis, another one for side channel analysis, and so on. And all of them are built on Symbolic Pathfinder. So ideally, we should also transfer them to the new build system. And it would be a good exercise to see if we can do that. And the newest project is called NeuroSPF, and I list here the link. And there is also a link to YouTube on how to run it, which was created by Mohammad Usman, who is a PhD student at UT Austin, who developed this tool. And finally, I'd like to thank you for your attention. And we have 2 minutes for questions. Thank you.